Thanks for joining. I'd like to welcome you to this week's seminar in our COVID-19 Research Seminar Series hosted by the UCD Research Partners team. It's where we try and highlight, various different types of great COVID-19 related research that's taken place across the UCD campus internally and in conjunction with external partners and affiliated facilities. And this series kind of focuses on the various different types of research related to COVID-19 that spreads right across all of the UCD's 6 colleges. We kind of hope that by running this series and then highlighting the different types of work that's going on and having your engagement with the discussions in the Q&A, that might lead to a greater level of interdisciplinary sort of collaboration between everybody as well. As usual, our series takes place every Wednesday at 2 o'clock. And we'll continue now through Christmas into New Year. We have various people lined up into February and into March, and more people joining all the time. So please do stay with us as we continue forward. And at this point, I think we'll get started. Let me introduce and mention who our speakers are today. We have Dr. Kevin Nolan and Professor Ronan Cahill. And in terms of a bit of a background for each of them, I'll just say that Kevin has studied aeronautical engineering as his background with University of Limerick. And then he undertook his PhD at the Stokes Institute there and performed optical measurements of flows, exhibiting the genesis of turbulence. He subsequently worked at a biotech startup there for a year, developing analytics software and next generation PCR instruments. And then he moved to Imperial College London as a Muir Curie Fellow, where he revisited his investigations into the onset of turbulence before joining Bell Labs Ireland in 2012. And here he combined his expertise in turbulence and microfluidics for his work in a Horizon 2020 TIPS project. And then more recently in 2018, Kevin joined UCD, where he lectures in fluid mechanics in the School of Mechanical and Materials Engineering, and he continues to research microfluidic flows. However, during the COVID-19 pandemic, he focused his extensive optical imaging expertise on understanding the role of aerosols in the spread of COVID-19. He's worked extensively in the Mater Hospital with Professor Ronan Cahill and other specialists there to understand how they can continue to safely treat their patients. And Ronan Cahill is the Consultant General and Colorectal Surgeon at the Mater Hospital in Dublin, and he's a full Professor of Surgery at UCD. He's the head of section and subject of surgery and surgical specialties at UCD. He's also the director of the UCD Centre for Precision Surgery, and he leads the Mater's Digital Surgery Unit. He's over 250 peer-reviewed publications, and he's the clinical lead on a major DTIF Consortium Award on the future of colorectal cancer surgery, which is an international randomized control trial on image-guided surgery called INTACT, and a Horizon 2020 award called PORSAV. So without further ado, I'd like to mention that Kevin and Ronan today will be talking about their COVID-19 project that's on the advanced imaging techniques to fully understand the transport of virus in the air. And at this point, I'd like to hand over to Kevin and to Ronan to kind of tell us a little bit about this project. And welcome Kevin, welcome Ronan.
Thank you. Yeah, I suppose we'll make a quick start on this. So I got a phone call or a Zoom call, as all things seem to start nowadays, from Ronan right back in April to discuss some imaging of gas leaks, particularly in relation to surgery. So this is something I was very unaware of, something I didn't really have any knowledge of. But when we talk about keyhole surgery, we talk about the kind of procedure, this minimally invasive surgery. The important part of it is the inflation or the insufflation of the abdomen with carbon dioxide. And that essentially allows space inside for surgeons to work. So the cartoon here on the right, where we see a patient, their abdomen is inflated, and then these trocars are placed as basically access ports in the abdomen, through which then instruments like cameras and various energy devices for cutting and staplers and so forth can be inserted in and out, and then they can be manipulated and so forth. And when the COVID-19 pandemic hit, it had a massive effect on medical treatment worldwide. We had this huge risk of infecting vast amounts of hospital staff and then knocking out our medical system. And surgery in particular, this keyhole or laparoscopic surgery was considered a significant aerosol generating risk, because of the high pressure oxygen or high pressure CO2 inside the abdomen could cause a problem with aerosolation of bodily fluids being ejected through these trocars or these ports. It's already been known for some time. Ronan, at the time we started talking about this, he explained to me how the large amount of CO2 used was known to be a health risk. The amount of smoke that can leak out during cautery and other procedures using energy devices can also be a health risk to surgical staff. And this is primarily down to leaks that can occur in these devices. As the instrument is inserted, we can get a leak around the top. There's a little kind of a duckbill type valve, a rubber valve in there. We can get leaks around the incision in the patient. This is an image here taken us a few days ago using a porcine cadaver, where we were doing some imaging with one of our collaborators. So this is kind of the genesis of this work, and this is where the bulk of this work has been focused. We've also done some additional work with Professor Conan McCall and his colleagues in the area of high flow nasal oxygen therapy. So when we look at patients, particularly critical patients who are in the ICU, we talk about intubation and putting the patient on a ventilator. That's a particularly risky procedure, and once the patient's on the ventilator, it's generally not a good sign. What tends to have better patient outcomes is the use of so-called high flow nasal oxygen, where we put a patient on a very, very high flow rate of oxygen using a cannula device, much like this, which is essentially two prongs up your nose. It's quite a large diameter, so it's heated, warm oxygen, and it's essentially shoved up your nose at a flow rates of up to 60 liters per minute. So having used it myself, it's extraordinarily uncomfortable just for a few minutes, having to be on it for several days to keep your lungs inflated and keep you ventilated is quite difficult. And patients tend to pull at it, tend to interfere with it, and it can have a dramatic effect on the aerosol that you generate. So what happens is a paper here from 2016, we see the nose region here, there's oxygen being essentially driven into the nasal cavity, and much of it can come back through the mouth, depending on the patient's airway geometry, depending on how they open and close them. But we can get a large amount of aerosol collecting in the throat, high shear, output through the mouth, collect droplets, and it's like you're continuously coughing effectively. There's a large amount of airflow coming out there. So in terms of having a COVID ward with patients on high flow oxygen, this is a significant risk, and understanding it and mitigating it so we can use the benefits of this therapy without the cost is obviously of interest. We're probably all now familiar with this hierarchy of controls diagram. We've all seen it numerous times. And much of the work we've been doing since March, April and the Matters, we kind of covered a lot of these bases in many ways. Much of the public outreach work we've done has focused on PPE. And on encouraging people to observe social distancing. So these bottom two rungs here. So we've published a lot of videos and images showing how masks work. We've worked with different people and different specialists to show how they can use their PPE better. For example, with ophthalmologists, we showed that wearing a mask underneath a drape was a bad idea because the mask ended up scooping the air and turning it in the wrong direction. So people were able to change the way they work and modify and protect themselves with PPE. But now, as we mature the work, we're progressing on to engineering controls and elimination of the hazard. So our PORSAV project, which I mentioned at the start of the talk, aims to try to eliminate some of these leaks that we're seeing. So yeah, we're trying to tackle everything on all fronts in many ways. So the main technique we're using a couple of optical techniques, using infrared cameras, using lasers, and using old school classical physics. So I'm going to focus on two of them today. I'm not going to discuss the infrared camera work in the interest of time, but the Schlieren imaging is a very old technique. It's been around since the days of Lord Kelvin. And it uses a very, very straightforward optical technique using primarily mirrors and focused light and parabolic mirrors. So on the left here, we have a video that I recorded several years ago, something you do in the lab on a Friday for fun, of some popcorn popping, and this is recorded at 10,000 frames per second using a phantom camera. So we can see here the popcorn as it explodes. We see all these lovely little particles of popcorn kernel and droplets of oil flying through the air, and the Schlieren reveals the wake of these individual micro droplets as they fly through the air at these inertial speeds. On the right-hand side, then, this is an image from NASA from their what's called their Airbus platform. Instead of using mirrors, they use sophisticated image processing techniques. And there's the aircraft looking down at these two T-38s as they fly underneath, and it looks at this micro distortions in the desert floor beneath, and it uses that to extract features. So on the left-hand side here, what we have is a view which we can see in real time. We can put the camera into the display, and we can see what's happening in this image as an optical effect. And on the right-hand side, each frame here takes about an hour to process on a supercomputer to extract all these features. So there's a kind of a benefit to each. The one on the right, you can fit an entire aircraft into your image, and you can get very precise details over larger fields of view. And on the left, we see what we get. What we see is what we get. We don't have to spend hours processing it. How does Schlieren work? I won't spend too long on it, but briefly, we have two large parabolic mirrors. The parabolic mirrors have a focal length of about 2 meters. Between the mirrors, we place something warm. In this case, a candle. It might be a patient exhaling. We have point light source, which is slightly off center. That light source hits the mirror. We get a column of parallel light, which we focus down to a point on the other side. And at that point where that light is focused, the most complex component is a razor blade. Apparently, Lord Kelvin used Gillette's. And the razor blade, when it's positioned just at the point where the light is completely focused to a point, we see on the camera that's downstream a dimming of the image. And any light source that passes over our, in this case, our candle, will be deflected via Snell's law. We get a change in refractive index due to the heating of the gas. And instead of hitting the tip of the blade, the light will be deflected left or right. And in our resulting image, we see this beautiful example here of a Schlieren, of a cigarette lighter just releasing some gas pre-ignition. So that's how Schlieren works. So right at the start of the lockdown, I hired a van. I loaded up the van with all my lab equipment and moved it out to the Mater. This is the space we used in the Mater. This is the former operating theatres. I think they were up in use up to about 9 or 10 years ago. This is now part of Professor Cahill's digital surgery lab. So the space here to do simulated surgery, it's a fantastic space to have. So as you can see here on the left, I have mirror 1, mirror 2 here on the right. This is the same Phantom high-speed camera that I borrowed from Bell Labs for this work. We've used multiple cameras throughout this work, and this one has been excellent. Our LED light source here, very low power LED. This is not a laser or anything sophisticated, simple LED light source. So it's a very low energy technique that does no issues whatsoever. And then we just have a location here where we can test different subjects. So one of the first pieces of work we did was on this device known as the intubation box, which is essentially a very simply, very ingeniously designed device that's designed to be placed over a patient. It's a plastic box, laser cut, and quickly assembled. And the intention was that you place it over the patient, and you've got handholds up at the patient's head, and then the patient can be intubated and be worked on, and then protect the OR staff from any kind of aerosol. However, we found that it wasn't quite adequate. Depending on how the person coughs or exhales, in this case, the person is coughing, we see a very strong shear layer as fluid is leaking out here on the open side. This side here of the box is open. So we made some proposals to cover this side with a drape and so forth and published that. This then led to future other papers from other groups who cited us, and there's a lot of buzz and research about these boxes until eventually the papers that cited us and so forth became part of the FDA deciding to remove their approval for this device. So some kind of early impact of our work. And this is one of the very first measurements we did on day 1. But the bulk of our work has focused on what Professor Cahill is primarily interested in, and that is leaks due to surgery from these trocars, these types of plastic ports we shove into the patient's abdomen. And we've done most of this work on using porcine cadavers, although we have done some work with live surgery as well. And the interest has been, well, what kind of pressure, what kind of CO2 pressure in the abdomen is the most risky? What kind of procedure? Do we put a certain device into a certain type of port? Should we avoid putting small instruments into these larger ports, for example? So a large port here is about a 12 millimeter one, and we have a 5 millimeter one here. Should we avoid certain procedures? How do we minimize the leak? How long does a leak last for? What is the strength of the leak and so forth? And to do that, we use primarily Schlieren. So this image tri-pic here on the bottom, on the left-hand side, this is what the raw footage looks like. This is playing back at half speed. So this is recorded on a digital SLR. The Phantom camera went back, unfortunately. So this is at 60 frames per second, and we're playing it back at 30. And we can enhance that image just by using frame-to-frame differencing. So with this very simple image enhancement, and we get this very, very clear image of what's happening in the image. And then we use optical flow. Optical flow is a very, very powerful technique to track motion in video. And then we can use that and scale it, and we can get an exact measurement of or reasonably precise measurement of the velocity of the flow in this leak. So we can quantify the Reynolds number, we can quantify the strength of the leak, how far it would go, and so forth within this field of view. And we're now working with people in the School of Mathematics to actually perform computational fluid dynamic simulations of this, with this as a boundary condition, to see just how far these jets can propel particles. The important thing is that the Schlieren does not see the particles or any particles in the flow directly. It doesn't have the optical resolution for that. It's only showing you the gas leak, and any small particles therein will tend to follow the gas depending on their size. So of this work, we have about nearly 2 terabytes of video data right now. It's been a very, very busy summer. So huge amounts of videos. Each of these videos is only a few seconds long. So it gives you an idea of just how much footage we've recorded. So as I said, we can't see particles with this system. We can only see the gas leak itself. We're seeing the refractive index change of the gas. Large particles, yeah, we can pick them up, but they're difficult to discern. The best way to see particles in airflow is using a laser, particularly a laser sheet. So my PhD was spent doing particle image velocimetry, looking at airflow in wind tunnels. And in order to see what the flow is doing, we seed it with aerosol. We use an aerosol generator. We seed the flow with micron-sized particles because we know they follow the flow faithfully, and then we track them. So now we're kind of going to have an inverse problem here. Instead of having to use the particles to see the flow, we're using the particles themselves that they're doing. So it's an interesting shift. So we don't have a particle image velocimetry system here in UCD. It's something I've been trying to get my hands on. So hopefully we get funding some stage in the future for this. So what we're using is a simple continuous wave laser expanded into a sheet. And then we illuminate, in this case, either 5 micron particles from a commercial nebulizer, and then we can image those particles and see where they go. So here we see, for example, this is a video recording from live surgery. The laser we're using, you can see here, is coming over this gentleman's shoulder here, and it's actually a disco laser. A little battery-powered laser has a class 4 laser in it, and we can essentially use a single beam with a galvo scanner, and we can scan that laser into a sheet as needed. So it's very versatile, it's very portable. The Schlieren system we can't move into the operating theater during live surgery. It's too big, it's too bulky, it's just unnecessarily risky. The laser system, you pop it on a tripod and you set it up anywhere you like, and then you can walk around the room with a camera and image the particles as they're seen. In this case, we're using the latest Canon put us to the top of the waiting list to purchase one of their R5 cameras. So we can record video at 8K resolution. So just for reference, your TV at home might be 1080p, a full HD TV. 8K is 4 times 4 times. That's a 16 times resolution, or 4 times a 4K video. So 2 by 2 for 4K. So you can record 8K video at 30 frames per second with at 12-bit pixel depth, so enormous detail. Or we could shoot at 120 frames per second at 4K. So the ability to get very, very good detail to kind of resolve individual particles with this kind of camera setup. And it's a consumer camera. It's not one of the expensive lab cameras, which makes things very easy to work with. You might have seen posters of me around campus on the staff e-zine. I think it's on the top of the banner. So this was a video I recorded and myself and Ronan edited to share. It was the start of the second wave, and we were kind of conscious that I think people were starting to forget about the kind of severity of COVID-19. So I wanted to kind of create some kind of video just to remind people. And we've obviously seen all these kinds of things before, and there's loads of examples of this. We've taught kind of a homegrown one, just very honest, very clear. Here's just me coughing into the laser. You can see how many particles there are. Just to remind people just how far particles can go, and just remember to social distance and wear your mask. And this video was picked up. It was described as horrific by The Sun. It was published in the Lad Bible, the Irish Times, RT News. So I think we covered all the key demographics. So that was good to see that people were talking about it. Which is nice. So since then, continuing to work on the high flow nasal oxygen therapy, we've been trying to combine the laser imaging with the Schlieren imaging. So this is an image of me again on the high flow oxygen with Brian Murphy, one of the anesthesiologists in the Rotunda who's doing this work. And inset here on the bottom, you can see the corresponding simultaneous view of me on the outside. So you can see the amount of gas leaking out of me. And then on the large video here, which was recorded in 8K, in this case downsampled to 1080p, the images are inverted, the color is inverted to highlight the aerosol. Aerosol is quite hard to see against this black background, but if we invert the colors to be dark on a white background, just flipping the colors in video editing software, you can just about see the large amount of particles that are being expelled when I cough. Now this camera, we're still fine tuning the setup, but this camera is at an angle over my shoulder. So the distance here is reducing with the depth of the scene. So the laser source here is about 2.5 meters away. This is about 1 meter away. And you can see when I'm on HFNO and when I cough and when I exhale, the aerosol, which is being injected here, this is the aerosol generator here. This is a saline being pumped in line with the tube coming into my nose. I'm driving aerosol well beyond 1.5 meters. So it's, it's very, very important that we get the right PPE, the right way to treat patients on HFNO, because it has many, many benefits. And then the next step, of course, is to try and do some numerical analysis on this data. This is a video sequence from one of my students working with a company called Aerosol Shield. They have a tent, essentially it's a plastic tent made out of surplus plastic from the British Army, which they believe has some electrostatic effects, which might be able to repel aerosol and keep it away and back down onto the patient's clothing or onto their away from workers. So we're doing some work to see the effect of different amounts of electrostatic charge to control aerosol. So this is a tiny crop of the 8K video. We just take a tiny little postage stamp size region of the 8K video, and we can see all these individual particles. And by putting it through the particle image velocimetry algorithm, we can actually see the motion of aerosol. So this is work that's ongoing with students. I've had several of my final year project students working on projects like this, and we're all having a ball. And now finally, just to finish up, we have our H2020 PORSAV project, so the Protecting OR Staff from Aerosolized Virus. So this is funded to the tune of 2.2 million in collaboration with partners across Europe in industry and academia. And the purpose of it is to primarily to look at this leak trap and endotrap devices that have been developed by Cahill in conjunction with us in the Matter and UCD. The device, this is a prototype of it here. So the device is essentially two different kind of versions of it, can either sit around the base of the trocar or up on top. And it has internal geometry, which they've been fine tuning as they come to the Matter. And we use the Schlieren to essentially suck up and vacuum away all the internal leakage, any leaks that may occur. So the latest version seems to work really, really well. The first version was much bulkier, had limited geometry, but as we've had, given them feedback and as we've discussed the design, we've gotten much better aerodynamics inside. Part of this project then, of course, is to try and develop a hybrid Schlieren system to kind of marry the benefits of the NASA approach to what I classical approach, but still maintain the real-time setup. So this idea is a Schlieren system we can just pop up anywhere. It doesn't require me to come and spend 2 hours aligning. It just aligns itself, and it gives you a much larger field of view. And then this will be deployed as part of the clinical validation. So there's going to be the bulk of the budget is paying for the clinical validation, where we have several hundred patients being tested, and we test the leaks that get or do not get past these different devices. So this is an 18-month project, and it's really, really exciting. So we have a number of publications already published. There's more on the way. And finally, these are just some of the partners and collaborators and people we've been working with. So thank you to all of them. Thank you.
Great. Thanks very much, Kevin. That's really great. A lot of detail there. I'd like to start off maybe before we run out of too much time, but I don't know if yourself or Ronan want to address a question I have in relation to the kind of overall learnings for clinical care from this work, and kind of what sort of different applications might be there for the work that you're doing.
We've learned enormously from this, and Kevin Nolan has just been fantastic in this. From the moment we contacted him out of the blue, Kevin was in and over and his lab up, and it was just the best collaboration I think we've had. He's almost one of the reasons we publish so much actually is because everything this guy does works, and it just keeps getting better and better and better. So
Here's a compliment for you now.
yeah, it's a really great story of collaborating with senior academics, and Kevin's been a marvelous ambassador for UCD at the hospital and has worked with surgery, anesthesia, speech and language, radiography, physiotherapy, everybody. So it's hugely informed the local hospital protocols, which reassured staff that they would be safe in managing patients, and advised tweaks to our protocols about how to do this, because there was a huge amount of uncertainty and fear around the hospital, and it's terrific to have a real-time way of assessing people at work. It's just, I can't understate the enormous impact he's had in the hospital, which is a tertiary and quaternary referral hospital for people with COVID. To build up though solutions is terribly important as well, because apart from just showing the problems with current practices, we do really want to build the solutions, and some of them are within our control, how best to wear the equipment that's used. But other than them, we can influence with working with industry, who many of whom have been excited about this. Some have been not so pleased, and some have been very serious about taking on some of this work in building equipment and devices that might make work done of it. So it's terribly interesting. And even if COVID now goes away, and fingers crossed, we still don't want plume, chimney smoke in the hospital environment if it can be avoided. So there is occupational hazards with being exposed to smoke and particles, products of combustion as we use diathermy. So Kevin has really opened up this area of practice and innovation, and terrific if anyone watching might like to contribute or collaborate, because literally it's as simple as Kevin says, what you see is what you get. And once we see things, we can solve things. And it's really, the hospital has been great too for allowing research to happen at a time when society was shut down. A lot of academic campuses too did not want this work to happen. But we know that it's terribly important to be empiric and evidence-based in our practices. And really, Kevin's just been a fantastic person.
Did you find that there was challenges then in setting up the lab at the hospital, considering the times we were in at the time?
Kevin, you can speak to this, but I think it was just open doors. Once you've got your van, once you got the equipment packed up.
Yeah, I was cruising around Dublin in a van in the middle of lockdown. It was quite interesting because of that unique space you have in the Mater, Ronan. That old part of the Mater, those old theatres, are now transitioning into laboratory space, and a lot of the teaching had stopped. So that part of the hospital was almost abandoned for people. So it was almost like an empty space we could move into. And then the people who were there managing it were just fantastic and letting us get things set up and giving us what we needed to get off the ground. So it was almost a perfect storm of getting things running and the space being available and having everyone being on board promoting the work.
And then for a while we flipped you into the actual current theatres too, which is just terrific. You know, that the hospital crisis management teams would include this work on the minutes of their meetings and give the approvals. And you see that there's a lot of names listed in the authorship. You need, Kevin, as you know, experts to work together to solve serious problems. And I think, there's been no shortage of people from within our institution and from other institutions coming to kind of learn, understand, and solve the problems.
Yeah, I think certainly the biggest thing is people just coming to the lab space where Schlieren is set up and just asking a question and then seeing how it works and then coming back and saying, okay, can we try this? I want to put this volunteer on and see this effect. Because once they realize how, as you say, what you see is what you get, it is, they really, they buy into it, and they don't have to worry about using complex chemicals or any kind of tracers or markers. It's a very, very powerful yet old school technique, and then modern cameras just really invigorate it. So yeah, definitely it's the people we've worked with in the Mater have all been fantastic, and they've all been so eager to kind of get involved.
It sounds like it was a very strong collaboration between the clinical side and the academic side of things, which we always want to see more of, going forward. You turn around and you got 5 publications from the work in a very short space of time is obviously very commendable as well. That's fantastic.
Having new data has been terribly important. What happened in the medical literature was everyone just wrote opinion pieces. often helped with by company interests. And there was very little new data to come out. So just to be able to demonstrate the things that people are talking about was huge. Kevin, there's a question there from the floor, maybe.
Yep. They're wondering whether you have any way of quantifying virus in plumes, and also to measure what actual impact in terms of protection against the virus you are having. A two-part question.
Yeah,
we are working on that, yes.
It's a great question, and we've done some work with other bacteria in looking at settlement plates. But to actually use virus particles, ideally deactivated virus particles, is rather specialized in the type of equipment, and we're hoping with Erigen, Kevin, that could work. You know, so we can certainly track particles of same size visually, practically we can count them, but really doing some virus work would really make this very compelling, and I hope we're close to being able to do that. But Gerald, I'm not sure where you're working, but if you had capability to do that, fantastic.
Great. Do you guys have any advice for anyone who wants to get into this area, or welcome any further collaborations in this area?
Ask Kevin for a Zoom.
Just come and talk.
Yeah,
yeah, it's happy to help out. You know, conversations. You know, I know we're all probably sick to death of Zoom, but a phone call or an email, just come and talk to someone. You know.
Yeah, I think having a hypothesis helps. So if you had something you can communicate in a short way of what you want to test,
yeah.
or add to. Kevin's not just a medical photographer to kind of, you know, it's about actually trying to solve specific problems to it.
Yeah.
But it's very interesting. You know, often you meet with people to collaborate with, and they say, well, that would be great, but let's try and get some funding or whatever to do it. But actually, we've done this the opposite way around. By getting the work done initially, has built out then the publication record, the funding applications, and then the funding awards. All done very quickly at a time of great pressure and stress. So it's really interesting.
Yeah. Great. Yeah, no, it's very interesting. Like you said, in a very difficult time, it's achieved an awful lot, and it looks like it's great scope for further work and application. So, well done, guys. Well done. I'm just conscious that we're kind of running over time a little bit, so I might bring it to a close unless there's any other questions, quick questions. But we can revert to the COVID-19 Basecamp team that everyone who registered should have access to. If you want to pose any further questions, or alternatively, you could also email directly to our speakers. I'm sure they'd be happy to respond to you after the fact. So with that, I'd like to thank Dr. Kevin Nolan, Professor Ronan Cahill for taking their time today. I know they're very busy to speak about their research, and also thanks to our audience for your interest and for your question, Gerald. If you'd like to continue the conversation, like I said, move to the Basecamp team. And with that, I'd like to then also just point out that next week we'll have another seminar again, where we'll be speaking with Professor Eileen Gibney. She's with the UCD School of Agriculture and Food Science, and Eileen will be sharing with us her key findings from a national COVID-19 food survey that's just recently completed. So with that, I'd like to thank everybody, and hope everyone has a good rest of the week. Thanks very much, Ronan and Kevin.
Thanks, Kevin. Thanks, everyone.
Cheers.